Welcome to Talk Tensors.
Glad to be here for this one.
Yeah, it's going to be a really good deep dive today. We are unpacking a seminal, just absolute classic machine learning paper that honestly forever changed how computers see the world in real time.
It really did. It was a massive paradigm shift.
Right. And for you listening, today we are skipping the abstract level of fluff. We're getting right into the actual mathematical and architectural gears of a real breakthrough.
Exactly. No high-level summaries. We're getting into the math.
Because to really understand this, we need to set the stage for you. You have to understand the era this paper dropped in. Before this, the field of computer vision was basically split into two warring camps.
The speed camp and the accuracy camp.
Right. You had the accuracy camp using things like Faster R-CNN, and that used a region proposal network, resampled pixels, and it was highly accurate but agonizingly slow. I mean, we were talking a sluggish 7 frames per second.
Which is practically useless for real-time applications.
Exactly. And then you had the speed camp using YOLO, which stands for You Only Look Once. Now, YOLO was blazing fast at 45 frames per second, but it really suffered in accuracy. It only hit a 63.4% mean average precision, or MAP.
Yeah, and that 63% was a massive roadblock. Think about it. 7 frames per second with faster R-CNN is useless for a self-driving car. If a pedestrian steps out into the road, the car needs to know right now, not a fraction of a second later after calculating region proposals.
Right, it's too late.
Exactly. And on top of that, embedded systems just couldn't handle the heavy computation required for the accuracy models. But you also can't rely on a system that only gets it right 63% of the time.
You definitely don't want a car making decisions with a D- in accuracy.
Right. So the field was just stuck between these two compromises.
Which brings us to the core thesis of today's deep dive. This paper proved that you could eliminate the computationally expensive bounding box proposal and resampling stages entirely. They encapsulated all the computation in a single deep neural network, and by doing so, achieved both blazing speed and state-of-the-art accuracy.
It was the holy grail at the time, a single shot detector.
Exactly. So let's get into the architecture of this single shot detector. Walk us through the skeleton of the model.
Sure. So it starts with a standard VGG16-based network.
And that's pre-trained on the ILS-VRC CLS-LOC dataset, right?
Correct. But they don't just use it out of the box. They actually truncate the classification layers. They chop them off.
Because they don't need the final classification. They need the feature extraction.
Exactly. They keep the base to extract those rich, learned features. But the real magic is the auxiliary structure they add on top of it.
Multi-scale feature maps.
Yes, the multi-scale feature maps. They add these convolutional layers that progressively decrease in size. So you might have a layer that outputs an 8x8 feature map, and the next one is 4x4, and eventually it funnels down to a 1x1 map.
Why does that matter so much? Why the decreasing sizes?
It's all about how we perceive scale. Lower layers in a neural network, the ones with larger spatial dimensions, like the 8x8, they capture very fine details, so they are perfect for spotting small objects in an image.
Like a bird way off in the background.
Right. But the higher layers, the ones that have been compressed down to, say, 1x1, they capture global context. They see the big picture. So they are ideal for detecting large objects that take up most of the frame.
Like a bus taking up the entire street.
Exactly. By tapping into multiple layers at different scales, the network can naturally detect objects of wildly different sizes without needing to artificially resize the input image over and over.
Which saves a ton of compute.
A massive amount.
Okay, so that leads us to the secret sauce of this whole paper. The default boxes and aspect ratios.
This is where the engineering gets really elegant.
Yeah, so for you listening, imagine dropping a grid over an image. And every single intersection of that grid, you place several boxes of different shapes. That's essentially what these default boxes are doing.
Yeah, and the mechanics of it are fascinating. Instead of just guessing boxes randomly, they use small convolutional kernels. Specifically 3x3x kernels.
And what does that kernel do at each point?
At each location on the feature map, that little kernel predicts two things simultaneously. It predicts a category score, so what object is in the box, and it predicts a shape offset, which adjusts the box to better fit the object.
And they don't just use squares.
No, objects aren't just squares. They explicitly define different aspect ratios for these default boxes. They use ratios of 1, 2, 3, 1/2, and 1/3.
So tall and skinny boxes, short and wide boxes.
Exactly, to capture everything from a standing person to a parked car. And they scale these boxes mathematically across the different feature maps. The paper gives a specific formula for the scale, going from an S-min of 0.2 up to an S max of 0.9.
Meaning the boxes get progressively larger as you go deeper into the network.
Right. So on a lower layer, the boxes are scaled to roughly 20% of the image size. On the highest layer, they cover 90% of the image.
And the result of this math is that they get 6 default boxes per feature map location.
6 boxes per location across all those different multi-scale feature maps.
Which means if you feed this network a standard 300 by 300 pixel input image, it generates a staggering 8,732 boxes.
Yes, 8,732 predictions for a single image, all evaluated in one forward pass.
Which sounds completely insane. I mean, 8,732 boxes. How does the network even process that without breaking down?
Well, that's where the loss function comes in. The network has to learn how to filter all that noise and make accurate predictions.
Right, the math of the loss function. Let's break down equation 1 from the paper in plain language.
Sure, so the network has to balance 2 main tasks. First, getting the location right, and second, guessing the object correctly.
The where and the what.
Exactly. So the loss function is just a weighted sum of those 2 things. You have a localization loss, which measures how far off the predicted box is from the actual ground truth box. They use a smooth L1 loss for this, looking at the offset of the center coordinates, the width, and the height.
And then you add that to the confidence loss.
Right. The confidence loss is just a standard softmax loss over multiple classes. It penalizes the network if it's confident it sees a dog when it's actually a cat, or if it thinks an empty space is an object.
I'll interject here just to clarify for you listening. In that equation, there's a weight term connecting these 2 losses, denoted as alpha. The authors just set alpha to 1 via cross-validation, so it essentially treats both localization and confidence as equally important.
Precisely. It doesn't overthink the weighting.
Okay, so we have this massive beast of a network outputting 8,732 boxes. How do we actually train it? Let's talk about the matching strategy.
This is a crucial step. During training, how does the network know if one of its 8,732 default boxes is quote-unquote right?
Because it needs a target to learn from.
Right. They use a metric called Jacquard overlap, which is also known as intersection over union.
Basically, how much does the predicted box overlap with the real object's box?
Exactly. If a default box overlaps with the ground truth box by more than 0.5, so more than 50% overlap, it is considered a positive match.
But wait, if you have 8,732 boxes, you're going to have multiple boxes overlapping the same object by more than 50%.
And that is actually a feature, not a bug. This simplifies learning immensely. It allows the network to predict high scores for multiple overlapping boxes. It doesn't have to agonize over picking the single absolute perfect box during training. It just learns that anything with a solid overlap is a good prediction.
Okay, but let me point out a logical problem here for the listener. If you have 8,732 boxes per image, and maybe only 3 or 4 objects in that image, the vast, vast majority of those boxes are just going to be looking at empty space.
Background noise.
Right. They're negatives. Doesn't all that empty space just completely overwhelm the training process?
It absolutely would if they didn't implement a brilliant fix. They call it hard negative mining.
Hard negative mining.
Right. Instead of using all thousands of empty boxes to calculate the loss, they sort the negative boxes by their highest confidence loss.
So they find the boxes where the network was most confidently wrong.
Exactly. The boxes where the network was sure it saw something, but it was just empty space. They take the top worst offenders and use those for training, and they explicitly maintain a ratio of at most 3 negatives to every 1 positive.
3 to 1.
Yes. This prevents the overwhelming tide of background boxes from drowning out the useful signal, ensuring stable and much faster optimization.
That's incredibly elegant. You only learn from your biggest mistakes.
Exactly.
Now, we also need to talk about data augmentation. The zoom in and zoom out tricks this paper introduced, because dealing with different shapes and sizes of objects is notoriously hard for these models.
It is. So they employed a really aggressive random sampling strategy during training. They didn't just feed the raw images in. They would take patches of the image, specifically patches that had anywhere from a 0.1 to a 0.9 overlap with the objects.
So they're training it on tightly cropped snippets of the objects.
Right. Then they resize all those patches to a fixed size and flip them horizontally at random.
Which forces the network to recognize the object even if it's off-center or partially cut off or facing the other direction.
But the real masterstroke was the expansion trick, the zoom-out operation.
Because the model naturally struggles with very small objects.
Right, because of how much the convolutional layers shrink the feature maps. So to force the model to get better at small objects, they created this zoom-out operation. They would literally place the training image on a massive canvas that was 16 times the original image size.
And what did they fill the rest of the canvas with?
Just mean pixel values.
Yeah.
Gray space, essentially. And then they would crop from that massive canvas.
So the network is forced to look at this tiny, shrunken down original image lost in a sea of gray and still identify the objects.
Exactly. And that single trick, just giving the network more practice on artificially shrunken objects, resulted in a massive 2 to 3% boost in accuracy across multiple data sets.
That is wild. 2 to 3% from basically pasting the image onto a bigger blank canvas.
It proves how important data augmentation is. Sometimes the data pipeline is just as important as the neural architecture itself.
Okay, so they've built this incredibly fast single-shot architecture. They've trained it with hard negative mining and aggressive augmentation. Let's look at the benchmarks. Let's read the scoreboard and see the victory here.
The results were undeniable.
They tested it on the Pascal VOC 2007 dataset. And the 300 by 300 pixel model hit 74.3% MAP at 59 frames per second.
59 frames per second, let that sink in.
And the 512 by 512 model, the higher resolution version, hit 76.9% MAP at 22 frames per second.
Which is incredible. It outperformed Faster R-CNN's accuracy entirely while remaining drastically faster.
Yeah. All right, let's compare that to our baseline. Faster R-CNN was at 7 frames per second. This hit 59. And YOLO was fast at 45 frames per second, but YOLO was stuck at a 63.4% MAP. This paper jumped all the way to 74.3%.
It was a total paradigm shift. They proved you did not have to compromise. You could have real-time speed and state-of-the-art accuracy.
It's amazing. And bringing the paper's actual image data to life for you listening, the specific detection successes are just wild to look at the visual data.
The confidence scores are so high.
Yeah, there's an image of a pizza identified with a 0.96 confidence score. A person standing next to it at 0.98. In another image, there's a sandwich on a plate with 0.99 confidence right next to a bowl at 0.98.
The localization is incredibly tight.
And the animal detection is basically flawless. They show cows identified at 1.0 and 0.94 confidence, elephants at 0.98. There's an amazing shot of a dog catching a frisbee, and both the dog and the tiny frisbee are perfectly boxed in midair.
It's performing flawlessly in highly dynamic scenes. But it's also important to highlight the failures because they show the limitations of the logic.
Right, the humorous misclassifications.
Yeah, my favorite is the image of the boys playing field hockey. The system confidently boxes the field hockey stick, but labels it as a tennis racket with a 0.97 confidence score.
A 97% sure it's a tennis racket.
Right. And it's funny, but it makes total sense when you think about it. The network is confusing similar object categories that share spatial locations and context. A long, stick-like object held by a human on a grass field. The network has probably seen a lot more tennis rackets in its training data than field hockey sticks.
It's making a statistical best guess based on shape and context.
Exactly. It doesn't know the rules of the game, it just knows pixel patterns.
So we have the results. But what actually mattered? The authors ran ablation studies, which are basically controlled experiments where you turn off parts of the network to see what breaks.
These are always my favorite part of a paper. It proves what is actually carrying the weight.
Right. So what happened when they started removing pieces?
Well, first, they tested the aspect ratios. Remember, we had ratios of 1, 2, 3, 1/2, and 1/3. They asked, what happens if we remove the 1/3 and 3 aspect ratio boxes?
The really extreme, stretched out boxes.
Right. And performance dropped by 0.6%. Not terrible, but noticeable. But then they asked, what if we also remove the 1/2 and 2 ratios?
So now we basically only have square boxes.
Exactly. And performance drops another 2.1%. So clearly, explicitly defining those varied shapes is critical for accuracy.
And what about the multi-scale feature maps, the auxiliary structure?
This was the big one. They asked, what if we only use the final Conv7 layer for predictions instead of tapping into all those different multi-scale layers?
Just looking at the one-by-one global context layer.
Right. And the accuracy absolutely plummets. It drops from 74.3 all the way down to 62.4.
Wow. It drops a full 12 points.
Yes. That single ablation study proves that the multi-scale, multi-ratio approach is the absolute backbone of this model's success. You cannot get this accuracy without looking at the image at different structural depths.
Okay, so it's a brilliant architecture, but what are the blind spots? What did the authors get wrong or flag as a limitation?
They were very upfront about the network's known weakness, which is bounding box size sensitivity. Specifically, it struggles heavily with small objects.
Even with the zoom-out data augmentation trick.
Yes, even with that trick, it's still a fundamental limitation of the architecture. Small objects lack information at the top layers of the network. By the time an image is compressed through all those convolutional layers, a tiny bird in the background is basically reduced to 0 pixels of useful data.
So Faster R-CNN still competed well on tiny objects.
It did. Faster R-CNN's two-step refinement process, where it specifically proposes regions and resamples them, was still inherently better at finding microscopic details.
Right, but despite that limitation, the legacy of this paper is immense. Because you have to remember, 80% of the forward time for this model was spent just running the VGG16 base network.
That was the bottleneck.
Yeah, so this paper paved the way. Because once you swap out that heavy VGG16 for a faster, modern base network like MobileNet or ResNet, the speeds become truly astronomical.
It cemented this architecture as the absolute foundation for real-time mobile and robotic vision for years.
It's the reason your phone can draw boxes around faces in real time through the camera apps.
Exactly.
Okay, let's move into our novel Notions segment. Please note, the following segment is for entertainment purposes only and represents speculative extrapolation, not actual peer-reviewed science.
Time to get weird.
Time to get weird. Idea 1, dynamic receptive writing or semantic box generation.
I like the sound of this, so let's ground this in the paper's fixed default boxes. The original model applies a rigid mathematical grid of 8,732 predetermined aspect ratios to every single image.
Right, regardless of what's in the image.
Exactly. What if, instead of that rigid grid, the network utilizes a fast reinforcement learning loop to dynamically generate default boxes based on the semantic complexity of the first-pass low-resolution feature map?
So it takes a quick glance and decides where to spend its energy.
Yes. If the scene is a clear blue sky, generate 0 boxes. Don't waste the compute. But if it's a crowded city street, focus the box generation densely in that specific quadrant of the image.
How would we actually build that experiment?
The first experiment would be training a secondary lightweight attention network that precedes the base network. This little attention network outputs a density map that dictates where the aspect ratio computations actually occur.
So it's essentially routing the receptive fields dynamically.
Right. It could theoretically push the frame rate from 59 frames per second up to 500 or more frames per second simply by bypassing empty space computation entirely.
That is fascinating. Skipping the negative mining by just not generating the negatives in the first place.
Precisely.
I love that. Okay, idea 2, temporal single-shot synthesis. Basically 4D object detection.
Oh, expanding into time. The authors actually hint at using recurrent neural networks for video at the end of the paper. Let's take it further.
Right. What if the aspect ratio boxes weren't just 2D? What if they weren't just width and height? What if they included a temporal dimension, a velocity vector?
So a box that predicts width, height, and speed.
Exactly. For the experiment, you apply those 3x3x p convolutional filters across stacked frames of video, across time, and you replace the standard smooth L1 localization loss with a kinematic loss function.
A kinematic loss function.
Yeah, a loss function that heavily penalizes impossible physical movements between frames, so objects can't just teleport.
So the network wouldn't just detect the object in the current frame.
Right. It would output a unified bounding box that predicts the exact spatial coordinates of the object in the next frame before that frame even arrives.
It's predicting the future.
Exactly. Single-shot temporal synthesis.
I mean, if you could get the loss function right, that would revolutionize autonomous driving trajectory prediction.
Right. It's fun to think about.
Definitely. Which leaves us with a final provocative thought to chew on.
Let's hear it.
If we can completely bypass the human-like cognitive step of proposing a region to look at, which is what Faster R-CNN tried to mimic, and instead we force the machine to look everywhere at every scale all at once, like this model does this mean the most efficient AI architectures are the ones that behave least like the human visual cortex?
Wow. That's a deep one.
Yeah.
Are we holding AI back by trying to make it act human?
Exactly. Maybe looking everywhere all at once is just computational superior for a silicon brain.
That is something to think about. Thank you for joining this deep dive on Talk Tensors. As always, the link to the paper is in the description. Read it, study it, and remind yourself to keep questioning the assumptions behind the code. See you next time.